So in the previous video, we went through solving the logistic equation, which is a nonlinear first-order differential equation. And in this video, I thought I would generalize the concept of differential equations a bit further by introducing the concept of an exact ordinary differential equation. So far we have dealt with equations of the form dy over dx equals to some function of x and y. There's another way in which you can write first-order differential equations, and it is the following way. So you can have a function m of x and y times the differential dx plus a function n of x and y times the differential dy equals to 0. And this is another way in which you might actually see a first-order differential equation appear. So we say that a differential equation of this form is exact if the following condition is satisfied. So if we take the partial derivative of m with respect to y and the partial derivative of n with respect to x, and both of them are equal, then we conclude that this is an exact ordinary differential equation. So what that means in that case is that we can actually find an implicit solution, f of x and y, by either integrating m x y with respect to dx, and that would also imply that we have the other condition, partial derivative of f with respect to y would be equal to n equals to x y. Or we can integrate the function n with respect to y and have the condition reversed, which would say the partial derivative of f with respect to x would be equal to m of x and y. So either of them would give us the same solution. So how can we apply this? Well, first of all, we need to actually look at a ordinary differential equation in this form and find out whether it is exact or not. So in this example, I'm just going to introduce this equation. So it's going to be 2xy minus 3x squared dx plus x squared minus 2y of dy equals to 0. Now, is this an exact differential equation? Well, let's find out. Let's make this equal to m, and let's make this equal to n. So partial derivative of m with respect to y is going to be what? It's just going to be 2x. Partial derivative of n with respect to x is going to be 2x. So yes, this is an exact differential equation. Now the next step is, of course, finding the implicit solution to the differential equation in terms of the function of x and y. So to do that, we can either integrate m or x. Let's do m in this example. So m of x y with respect to x. And what's that going to be? Well, that's going to be the following. We're going to have integral of 2xy minus 3x squared dx. And that's going to give us x squared y minus x cubed plus some constant, but that constant is not going to be a single value. It's actually going to be a function of the other variable y, because we're integrating with respect to one of the variables, and this is a function of two variables. This constant is actually going to be a function of y only, because if we had any function that is a function of y only, then it would vanish as we take the derivative with respect to x, and that's why we have this term here. Now, obviously, we need to find the value of this, because this is not good enough for our solution. So what can we do next? Well, we know that if the differential equation is exact, as we just proved, then all we need to do is we need to apply a second condition, which says that the partial derivative of f with respect to y, because we integrate with x, so now we're just going to take the partial derivative of y, it's going to be equal to the function n of xy. And we know this from the problem. It was given as x squared minus 2y. So what can we do with that? Well, we simply differentiate this whole thing. So that's going to be what? That's going to be sorry, that's not going to be 2, that's going to be x squared. We're differentiating with respect to y here. So that's going to be x squared. This term is going to vanish, and this is going to become the derivative of g with respect to y. And that should be equal to n, so that's equal to this. So what happens here? Well, this cancels out, and we can integrate both sides with respect to y now to find what g is. So g of y is going to be the integral of minus 2y with respect to y, and that's going to be minus y squared plus some constant. And in this case, because we're integrating with respect to a function, a single variable, our constant is just going to be that, a constant. So in the end, what you're going to have is final result is going to be x, y is going to be equal to x squared times y minus x cubed minus y squared plus c. And that's going to be the general solution to this equation. Now you might be wondering, why do we have a solution that is actually a function of two variables instead of one? I mean, we know that y is a function of x, so it seems kind of weird to have this kind of expression come out as our general solution. But the fact is that with this type of differential equation of this form, we can only hope to get an implicit solution. So because we cannot really separate m from n, we are always going to end up with an expression like this. And we can still do stuff with this. Like, I mean, if you plot this on a 3D plane, that's going to be, sorry, not a 3D plane, a 3D graph. So set of axes like that. Obviously, this is going to be the height of that function as a function of x and y. But you can look at the plane x and y to find out the relation between the two. And that's essentially how you would look at the solution of a function like this. Now, this doesn't actually occur very often in physical problems, so we don't have to worry too much about it. But it's just an important remark to make that there are differential equations that are expressed in this form. And this is essentially how you would go about solving them. In the next video, I'm going to talk a little bit more about first-order differential equations, and I'm going to introduce something called the integrating factor method.